So that brings us to the meat of our discussion today, which is, first of all, what is a force? So far in this class, we have been talking about how things move. So if we just take for granted that an object has a certain acceleration, it has a certain initial velocity, we can go ahead and calculate where it's going to be at a later time and how fast it's going to be moving at a later time. But the deeper question is, why did it start moving with that initial velocity? Why does it move under a certain acceleration? And that's where chapter 5 comes in, which I assume you have all at least skimmed by this point in our journey. So a force is just something that causes a change in velocity. So forces cause changes in velocity. Right? At this point, we don't know a lot about forces. We just are going to say that a force is the name that we give to whatever causes things to change their velocity. And in fact, that brings us to Newton's first law. So Newton's first law is a kind of restatement of this definition. So what it says is that the velocity of an object is a constant unless there's a force. Okay, so things move on their same path at their same speed forever unless something stops them. And that something, we're going to call that a force. We have any questions or comments on just this definition, this beginning discussion? How do we find n? Yeah, Michael, you are a step ahead of us. So once we have defined what a force is, how do we do math on it? Well, we have a couple of things that we want to mention there. First of all, just from our everyday experience, we know that bigger things are harder to move. So instead of just talking in terms of accelerations and saying accelerations come out of nowhere, like accelerations are the fundamental thing, we make this postulate and say that the thing that's causing movement, which is forces, it will in fact produce an acceleration, but the mass of the object being accelerated matters. That is, if you apply the same force, the same amount of effort to a more massive object, you get a smaller result. And that meshes really well with our intuition about the physical world, right? We, at this point, you all have lived in the physical world for something like 20 years, so you have an idea already for what happens when you shove things. And So we want to make the point that Newton's laws, they don't come out of nowhere. They're not magical. They are a mathematical way of writing down in a precise manner what we already know about the physical world. So, since bigger things are harder to move, we're going to say that mass is a proportionality constant, which actually kind of just moves the goalposts back, because now instead of answering what's a force, we have to answer what's a mass? Like, what does mass even mean? Anyone want to take a shot at defining mass? Well, kilograms, that's how we measure mass. But what is it, like at a fundamental level? All right, so Eric says mass is the amount of matter an object contains. Sure. That just moved the goalposts back one step further. What is matter? Right? Cortez says a measure of inertia. And that is probably the best answer that we can give at this level. Mass is a measure of an object's resistance to being accelerated. So sure, we can say something about, like, well, mass is like an indirect way of counting how many protons and neutrons are in an extended object. And yeah, we could say that, but since we don't walk around with, scanning, tunneling microscopes everywhere, that's a pretty unwieldy definition of what mass is. So instead, we're going to say, well, mass is just an object's resistance to acceleration. We know that some objects resist acceleration more than others, and we're going to call that resistance mass. The other thing that we want to note is what happens if there's more than one force trying to change an object's velocity at once. Well, we already know a bit about vectors. So a force is a direction and a magnitude, which we know it is, right? Because if you push something to the left, it's going to accelerate to the left, right? You can't shove something to the left and have it fly up into the sky. That's just not how anything works. So once we have the idea that forces are parallel to accelerations and that mass is the proportionality constant between those two, it actually becomes pretty simple to add up multiple forces, right? If forces and accelerations are linearly dependent on one another, then what happens if we have two forces? Well, we know how to add vectors. So we're just going to apply what we know about vectors to forces. And we're going to say that, yeah, forces are vectors. They obey all the mathematical rules that we've already established. And more generally, we're just going to say that if we have some number of forces acting on an object, that if we sum all of those forces up, then what we will get is the net acceleration of an object times its mass. This is what we call Newton's second law. And it's going to be the workhorse of this class for at least the next 6 weeks, just like Kinematic 2 has been our workhorse for the past few weeks. In fact, it's so important, we're actually going to add it to our toolbox, like officially add it to our toolbox. So here's an updated list of tools. We have our kinematics. So a kinematic describing velocity as a function of time. A kinematic describing position as a function of time. And a third kinematic, which is time independent. We also have centripetal acceleration. So for things moving in a circular motion, their net acceleration has to be equal to v squared over r, and it's going to be toward the center. And now we are going to add Newton's second law to this list. All right. Any questions so far? Newton wouldn't have used vector math initially, right? Well, actually, this concept, like the basics of what we call vector algebra now, goes back to the time of Euler, Leonhard Euler, and he lived. He was born in early 1700s. So Newton had something like vectors when he was formulating Newtonian physics. So of course the form that we use them in today, it was finalized in the late 19th century, so like 1880 or so. But yeah, the origins were hundreds of years before that. But great question, Eric. All right. I would like to do a few problems using, to kind of illustrate the vector nature of forces. If no one else has any questions on this topic. Okay. Let's do some problems from the book. We're going to start with pushing a cart. There are a certain number of toy problems that we handle in physics, and one of the things that we're going to come to over and over again is pushing a box, right? We're going to draw things as boxes. We're going to analyze what happens when they get pushed, what happens when there's friction on them, what happens when they slide down a hill. Physicists just love boxes, mostly because we can't draw. So here we have a laundry cart, which is a fancy word for a box. And we have someone pushing the laundry cart. Okay, pretend arms are really that length. Um, when we're dealing with forces, we want to modify a little bit the way that we have been drawing pictures. Because now we want to draw the picture in such a way that all of the forces on the object in question are specified. So we have this laundry cart. We have a dude pushing it. So there is going to be a force on the object to the right. And real quick while we're here, specify our coordinates. Is this the only force on the cart? McHenry, no. Morales, no. Yes, you guys are correct. The force of the dude pushing the cart is not the only force. What are we missing? Jaden McHenry says friction, and that's true, but we're going to leave that till next chapter. So if there is no friction, yes, Matthew Keys, gravity. We are missing the weight of this cart. So for now, we will assume that there's no friction involved, but don't worry, we're going to get there in chapter 6. So we have some weight to this cart. If we know that the laundry cart is 4.5 kilograms, can we calculate the force of gravity on this cart? Do we have enough information? Anybody? I haven't heard from Latif, from Calderon, from Diawara, from Davis, from Cruz. What do you all think? Can we calculate how much force gravity must be exerting? Yeah, we totally can. Because remember, a force produces an acceleration on a given mass, right? So remember, here's how we define a force. So if we know the mass, we also know the acceleration caused by gravity everywhere near the Earth's surface. We've been calling it g. So the acceleration, g, times the mass of an object will give us its weight. And that is the force that gravity exerts on this cart. So we can totally calculate that. So now our diagram is mostly complete. So we've drawn a picture, we've specified the coordinates. Let's break down these vectors. So we're going to call the pushing force P, and that's 60 newtons in the x direction, nothing in the y direction. We're going to call the weight W, and it's nothing in the x direction, and it is negative mg in the y direction. Okay. So now we can reach into our toolbox, and since this is chapter 5 and it's about Newton's laws, chances are good that we are just going to go ahead and use Newton's second law to answer this question. Just like in kinematics, there's two scalar equations hidden inside this. We've already broken down these forces into x and y components. So in the x direction, we have only one force in the x direction, right? So on the left-hand side of Newton's second law, it says sum of forces, right? And when we apply that, we literally are just going to sum the forces in that direction. So here, the sum of forces is 60 plus 0. And on the other side is mass times acceleration. So 4.5 is the mass and acceleration in the x direction. So that lets us easily say what the acceleration in the x direction is, right? It's going to be 60 divided by 4.5. Now, those of you who are looking ahead might be asking, well, what's happening in the y direction? Anyone spotted the problem in the y direction? So, Kyle Pullercat, what's wrong with this? When we solve for for ay, the acceleration in the y direction, is this right? I mean, if you are pushing a cart along the floor, does it sink into the floor due to its own weight? Yeah, no, that doesn't happen. So that tells us, you know what? We must have forgotten a force in our original diagram. And in fact, we did. There's something we call the normal force, but I like to call it the anti-squish force. So surfaces will exert a force against objects in order to keep themselves from getting squished. So the surface, whether it be a floor or a ramp or a chair, things don't like to get squished, and they will push back to keep that from happening. So there is actually another force here, and we call it the normal force, and in this class I'm going to be denoting that little n. So little n must be operating in the positive y direction in order to counteract the weight that's acting in the negative y direction. So we're just going to go ahead and specify it like this. And then if we reanalyze what's going on in the y direction, we write down the sum of forces. So we have 0 minus mg plus n equals mass times acceleration in the y direction. And since we're applying our common sense now, what is it the acceleration in the y direction should be? Like, what should the net acceleration in the y direction be? Yeah, Eric Ramsey, you are correct. It should be 0. right? We do not expect the cart to either sink into the ground or fly off into the air. We expect it to stay on the ground. So we set this whole thing equal to 0. And that tells us that in this situation, the amount of normal force that the surface is exerting is going to be equal to the weight of the cart. And that is actually an important result because it gets us to Newton's third law. You may have heard Newton's third law stated as every force produces an equal and or every action produces an equal and opposite reaction. And that's what we just saw there, actually. So if two things are in contact, if one is exerting a force on the other, right? So we'll call these object A and object B, and somehow they're exerting a force on each other. Either one is shoved up against the other, or there's magnets or something. I don't know. It doesn't matter how the force is applied. But the force that A is exerting on B is going to be equal and opposite to the force that the force that B is exerting on A. And what's the meaning of this negative sign here? Like, why did this negative sign slip in? The negative sign there is just for direction. So the negative sign just says that this vector, right? So is this vector F from B to A is pointing in the opposite direction of the other vector F from A to B. So A is pushing to the right on B, B is pushing to the left on A. And this is the essence of Newton's third law. All right. Eric Ramsey asks, if it's a slanted surface, the normal force would be different. That is correct. So we will definitely be analyzing that in more detail in Chapter 6. In fact, the box on a ramp problem is one of the most iconic problems of basic mechanics. We are going to spend an entire day just looking at boxes on ramps. Matthew Keys, except for when we both start rapping. Is that an Epic Rap Battles of History reference? Yeah, well done, sir. All right. So, today we have gone over Newton's 3 laws. Which one of these has what I'm looking for? Here we go. All right, so Newton's first and third law, they don't usually make it onto our list of tools because they don't help us calculate things. We may certainly use these for arguments. Like we might make an argument about why two forces have to be the same and call upon Newton's third law for that. But in general, they don't help us calculate things, so I'm going to leave them off of our toolbox for now. Do we have any questions on Newton's three laws? Okay, let's do another problem. We're going to look at question 32. Suppose two children push horizontally but in opposite directions on a third child in a wagon. First child exerts a force of 75 newtons, the second a force of 90 newtons, and friction, which we know exists, but we haven't really specified how to deal with it yet. So friction is going to be 12 newtons. Mass of the third child plus the wagon is 23 newtons. Okay. So we have a few things to talk about here. So first of all, when we have friction in play, what direction does a frictional force push? Anyone want to make a guess? Matthew Keys says opposite to the motion. That's right. So friction will push against whatever direction an object is moving. But the other thing to keep in mind is friction is something that happens between a surface and an object. So if our surface, is down here, this black line, friction can only be parallel to the surface. So it can't point up, it can't point down, it can only point along the surface. All right, so let's draw in the forces here. So the first child exerts a force of 75 newtons. The second child exerts a force of 90 newtons, but in the opposite direction. And since the second child is pushing harder, we presume that if there's any motion at all, it's going to be to the left. Which means that friction will point to the right. And of course, we're going to have the weight of this whole thing. Palencia asks, is air resistance a form of friction? That is an excellent question, and yes, it can be. There is some difference going on there. So we will talk about that more next chapter, but in general, the friction between a surface and an object only depends on the materials involved, whereas the amount of air resistance that an object experiences depends on its shape, its volume, and its speed. All right, so here's our picture. We're going to specify our coordinates, positive x, positive y. And the first push is happening in the positive x direction, nothing in the y. The second push is happening in the negative x direction, nothing in the y. Friction And I usually use a scripty F for friction just because capital F is already used for forces. So scripty F will be my friction symbol. And it's going to be acting in what we've drawn as the positive direction. And the weight is going to be nothing in the x direction. Have we gotten all of the forces involved in this situation? All of the forces on the cart, I should say. McHenry, you are correct. We have not written down the normal force yet. And there must indeed be some normal force. All right. So there's our vectors broken down. We would like to now, so first of all, like we're going to be looking for the acceleration of the kid in the cart. That's going to be our final goal. So whenever we're starting a problem, one thing that we kind of implicitly have to decide in our pictures when we're drawing our diagram is what is the system that we're interested in looking at and what comes from outside the system. So this gives us a good chance to talk about that. So if we're interested in the movement of the cart, then the system we're interested in is the cart. So we're only writing down forces that are on the cart, right, and the little kid inside of it. Cart, wagon, crate, whatever. Box and person. Now this orange fellow on the left is pushing with 75 newtons of force on the wagon. Newton's third law says that the wagon is also pushing back with 75 newtons of force on the orange fellow. But we don't care about that because we're not interested in the movement of the orange fellow. We're interested in the movement of the cart. So there is, in fact, a 75 Newton force pushing on the orange fellow, but that's not part of our system. Likewise, the orange fellow also has his own weight and his own normal force, but we aren't concerned with that. The orange fellow is not in our system. It's just the red wagon and kid. So just the red stuff is our system. Everything else is external. All right. Let's talk about forces that are internal to our red, though. So, there are forces between... So there's two objects in our red system, the kid and the wagon. There's going to be a normal force between them, right? So the kid is exerting his force on the wagon. It's in fact... Let's draw that out. So here's the bottom of the wagon. Here's the kid sitting on it. There's going to be, on the kid has a weight going down, and the wagon is going to, so this is mass of the kid. The wagon is going to be exerting a normal force. This is normal force from the wagon to the kid. So why don't we draw those in? Why aren't those important? Anyone have a guess? So Eric said the problem gave us the mass of the child and the wagon put together. That is correct, it did. Which was a clue that the wagon plus kid was the system that we needed to be interested in. But just because these internal forces are inconvenient for us, right? Does that mean we get to ignore them because they're inconvenient? The real issue here is that the normal force of the wagon on the kid and the weight of the kid form an action-reaction pair. So Newton's third law is going to tell us they're equal and opposite. More importantly, they are internal to the system. So they're going to cancel out, right? So if internal to the system we have pairs of forces that cancel out, their net effect is zero, right? So if we were to write down, right, the forces, sum of forces in the y direction for our wagon and kid, we would write down, well, mass of the kid times gravity in the minus direction, and then mass of the wagon times gravity plus the normal force from the wagon to the kid plus the normal force from the ground to the wagon. This actually gives us an indication of maybe one change we should be making to how we write down Newton's second law. Only forces that come from outside a system can cause acceleration. So external forces cause acceleration. Internal forces do not. Is there any way that the kid in the cart could push on the cart and make it move? Right? Put another way, is it possible for you to lift yourself by your own feet? Like, can you reach down, tug on your feet, and pull yourself into the air? Is that possible? No, that's not possible. So forces that are inside a system can't move the whole system, can't move the system as a whole, right? And that's not just our application of common sense saying that. That's Newton's law, Newton's third law, coming in and saying, yeah, actually, these are going to be equal and opposite, so when we sum them all up, they're going to cancel out. So, two ideas. So one, forces that are internal cancel out. Forces that are external cause acceleration of our system. And forces on other objects, in this case the orange fellow and the pink fellow, forces on other objects don't matter. right? Force. So principle one here is an application of Newton's third law. Principle two here, well, that's just Newton's second law, and principle three here is just limiting our scope, right? We don't want to have to consider the entire universe every time we want to solve a physics problem. So we have to be able to limit our field of vision. We draw a box around what's important for this analysis, and we just focus on that, right? And then forces that are on external objects, we don't care. We're just looking at what happens in a specific place and time. Any questions about what I've written down so far? Questions, comments, memes? Okay. So let's finish this problem off. So part A was the very detailed discussion that led us to these three principles. Part B is what I call the SUAC, the shut up and calculate. So for that part, we're gonna pull out Newton's second law. Sum of forces equals mass times acceleration. And in the x direction, that's going to be, you notice all these vectors I wrote down in green? Right? There's a reason that I write them in a vertical orientation like this, because we're going to want to sum them all, right? So this makes it really easy. So it's 75 minus 90 plus 12 plus 0 plus 0. So in the x direction, we have 75 minus 90 plus 12 equals mass times acceleration in the x direction. And what is the mass of this thing? 23. Notice I'm actually being a tad bit sloppy here, because my normal rule is don't plug in numbers until the very end after you've done all your algebra. So let me actually rewrite that. We want to make this clean. So sum of forces in the x direction is p1x plus p2x plus friction, and that's going to equal to m times ax. In other words, the acceleration in the x direction is equal to p1x plus p2x plus f sub x all over m. And now we can plug in numbers. 75 minus 90 plus 12 all over 23. It ain't much. So this gives us minus 0.13. What does the minus sign in our answer mean? Right, I think, Katja, what is the, I think you're the only one I haven't called on yet today, this week. What does the negative sign in our answer mean? Nope. Okay. The negative sign just means it's going to the left. Right back in step 2, we decided to define to the right as the positive x direction, which means that when we come down and we get a negative answer, it's going to the left. So we are accelerating to the left in this problem. All right. And then part C, what would the acceleration be if friction were 15? Well, then we'd have 75 minus 90 plus 15, and we'd get a big old 0. So there'd be no acceleration at all. Any questions? Eric, so we're just assuming friction is pushing to the right here. So yeah, at the beginning of the problem, I looked when we were writing down our forces, I noticed that we had 90 newtons pointing to the left, 75 newtons pointing to the right. So if there was going to be movement, the movement would be to the left, and friction goes against movement. So then, so friction's going to go to the right. Now when we came down to it, if I had gotten a positive number here for acceleration, I would have said, oh, whoops. If this thing is actually moving to the right, that means friction's not going to the right at all. So I would need to go back and I would need to correct that assumption. Does that answer your question, Eric? Yep, okay. Matthew says, what is that first part being divided by? On the bottom here with a sub x, that's the mass of the whole thing, right? Which is our 23 kilograms. Wilver says you would need to correct the assumption, but the math pretty much stays the same, right? Yep. So if we went back and we changed our assumption about which direction the friction was pushing, we would just go ahead and boop, change this plus 12 to a minus 12. And then we would finish off the last step again. All right, any other questions before we wrap this up? I think this is about it for today. Yeah, I'm still going to go over the quiz, so hang around if you want to see the solution to the quiz. Otherwise, we're done with new material today, and if you think you aced the quiz, then peace, and I'll see you on Monday. But yeah, if you want to see the quiz answer, stick around for a minute. Alright, so for the quiz, we're looking at number 94, which is from the additional problems section in chapter 4 of the OpenStax book. So the maximum horizontal range of a projectile, which is launched at 10 meters a second, is 20 meters. So what's the acceleration on this strange and distant planet? So first we're gonna start out drawing a picture, just like always. Here's the ground. Here's some potato cannon of some sort. This thing gets launched at 10 meters a second. The angle at which it gets launched, we're just going to call theta for the moment. And this thing will land somewhere over here, a distance x away. Right, we're going to specify our coordinates, x and y direction. And then we're going to say, well, what does it mean if we're talking maximum horizontal range? If you want maximum range on a projectile, what angle should you launch it at? Yeah, exactly, Jaden, 45 degrees. You should launch it at 45 degrees. All right, so there's steps 1 and 2 out of the way. Let's write down our vectors. So we're going to have our initial position. We're just going to call that the origin. So the cannon is at the origin. The final position will be a distance x away, but at a height of 0, right? Because it's going to be on the ground. The initial velocity is going to be 10 cosine 45 degrees in the x direction, 10 sine 45 degrees in the y direction. Is anyone confused about where the cosine and sine came from? The acceleration is going to be negative g. We're not writing negative 10 because we don't actually know that it's negative 10 in this situation. All right, so there's our vectors. What physics are we going to use to analyze this situation? Well, let's take a quick look. Nope, not that one. Not that one. That one. We've got initial and final positions. We've got initial velocity. We've got acceleration. So it looks like to me it's going to be K2. Right? Our workhorse K2 is going to help us analyze this situation. All right. So first we'll write down our general equation just to jog our memories. Okay. And let's take a quick stock of our unknowns. Here our x is actually known, sorry. Our x is 10. So our unknowns are going to be our t and our g. And it's unusual that g is our unknown, but it's not any more complicated algebraically than if t and x were our unknowns instead. Notice also that 10 cosine 45 is just a number. Like, it's going to be 5 square root of 2. And the same for 10 sine 45. It's going to be 5 square root of 2. So those are just numbers. All right. So let's take a look at the x and the y direction here. So in the x direction, we have our final position is going to be 10. That's going to equal, the initial x position is 0, so we have our v naught t term. So 10 cosine 45 is 5 square root of 2 times t. Matthew, you're exactly correct. X is 20, not 10. Initial velocity is 10. Okay. So this lets us solve for t. So t is equal to 4 over square root 2. And if you like, we can simplify this, because having radicals in the denominator is aesthetically unpleasing. So we can multiply this thing by radical 2 over radical 2, which is equal to 4 radical 2 over 2, which is equal to 2 rad 2. All right. That's a whole lot more aesthetically pleasing than 4 over radical 2. So then we can go to the y direction. So y, the final y position is 0. Initial y position, also 0. The initial velocity times time term. So we have plus 5 square root of 2 times the time, which is 2 square root 2. And then minus 1/2 g t squared. We'll do some quick simplification. 5 square root of 2 times 2 square root of 2 is 10 times 2, or 20. And then 2 square root of 2 quantity squared is 4, 2 squared, 4, square root of 2 squared, which is 2. So it's 8. So we have 8 over 2, which is 4 times g, so minus 4g. So 0 equals 20 minus 4g. In other words, g is 5. Questions or comments? Anybody need some clarification on this? Glad it helped, Zerby. Eric, you use the range equation given by the book. Is that fine? Yeah, but it's, against the spirit of this class, right? We want very few tools, and we want to use those tools to analyze. So if you're adding more and more specific equations to your memory banks, right? You can only do that for so long. Because there's just too many situations that we need to analyze. So memorization of more formulas is not as good as getting practice manipulating our toolboxes. But yes, it'll give you, you'll get full points if you wrote down the range equation from the book. Yeah, have a great day, y'all. Enjoy your weekend. Do lots of physics, and I'll see you next week.